think we probably should.
Are there any news?
I typed the random extension on Friday. It's so many types.
Oh shit! Thank you for providing. Thinking about you probably can leave sleeping and drink on Wednesday. Probably in OHD.
Any other news? Are you sharing?
Yeah.
Hello. Can somebody hear me? Yes.
What's the question?
My bad indeed. Not my only one, I'm afraid.
Yeah, we're all good.
So,
Okay, perfect. Thanks for inviting me. Thanks to the organizers to giving me this opportunity. Excellent. So today's 101 is actually a proper 101. And as 101 goes, it was almost well prepared. But then it was well prepared, but not really as a talk. So I think the talk will be well unprepared in the sense that I looked quite a lot into the various algorithms, but forgot to make slides and forgot to actually write down what I was reading. So it will be a bit of an adventure, but let's see. So I'm talking about something that is not something new, but something that is very much at the heart of a few things that I'm busy with. And I always avoided looking into it because it's a bit technical, just to solve, basically to solve a certain problem, namely parity games. So parity games, as we will see, are a nice formalism to talk about fixed points. And then you can just be the user, so to speak, and say, okay, fine, I know that parity games are determined, that's good enough for me. I don't really need to know how you can prove this and how you can compute it. And not always, but to a large extent, I was always trying to be on this side because I somehow was slightly afraid of parity games. So this is a talk to kind of get rid of this problem of mine. I also, the talk goes also back, in fact, to Sean, who is not even in the audience now. Is he in the? No, he's not. I think if you are now horribly bored by this talk, you should also complain to Sean, because we had a conversation. He was asking me this question: how do you actually compute this? And then he said, "Oh, wouldn't it be nice to give a talk about it in the 101? Here am I giving a talk in the 101. Okay, so it's really a 101 in the sense that it's nothing I did. It's just something other people did, and I want to talk about it. The connection to the general programming language, if people are eager to know a programming language connection of this talk, then this is the talk that got me as close to popular as I ever will get, I think, because I gave the first part of this talk that I'm about to give now about the fixed point games, and somebody went away very happily of finally understanding the fixed point games and wrote a paper to Popple about it. And I'm in the acknowledgements saying, thanks for Chris Kupke to give this talk, because anyway, but I mean, I'm not claiming authorship of the paper, but anyway, I was kind of very much moved to see myself in the acknowledgements. Okay, good. This is about graph games. So the first, let's say, maybe 20 minutes is relatively informal, and it's just about setting the scene for the parity games. So, okay, consider this. Consider a monotone operator on some complete lattice, which happens to be the lattice of all subsets of a given set X. Why are we interested in this lattice? It's about, I mean, I'm coming from the logic direction, where we're talking about the meaning of a formula being such a subset. And then you can, certain formulas give rise to these operators, and then you can enrich your language with fixed point operators that would then take the fixed point of these operators. So looking into this particular type is just coming from logic or modal logic, if you wish. And okay, so once you have a monotone operator, you know from back in the days that the collection of all fixed points actually forms itself a complete lattice. But in particular, it has the least and the greatest fixed point, or largest fixed point. And we can not compute them like this, but characterize them like this. So the least fixed point can be characterized as the smallest prefix point. So this thing, if something is of the form, if you have a set that's satisfying this, f applied to that set is included in it, that's called a prefix point. It does something. It's alive. Okay. This is a postfix point, and the largest fixed point is the greatest postfix point, and the least fixed point is the least fixed point is the least prefix point.
You can get your next slide.
Whoa! How does this even work? Anyway, it's a mouse. Okay, good. Okay, I don't know. So the first 10 slides are a bit older. I don't know what I wanted to say here. Co-induction. So this is the co-induction proof principle, basically, saying that any set that is a solution of the same. What am I talking? Forget about it. I don't want to make any sense of this now because this is a way of defining the least and the greatest fixed point. It's not a very useful way. There's another characterization of those, and this is the one that we are more interested in, namely using this fixed point approximation. So this, I usually, there's a small chance that I confuse the two. The thing that you saw on the previous slide, I think is Knaster-Tarski. This one is Kleene's theorem, that you can approximate the fixed points in this chain. To be more precise, Kleene's theorem, I think, only goes to here, so to speak, the original one. And then there was some paper in the 70s by two French guys who had both the same last name, Cousseau, who extended, yes, who extended it to arbitrary ordinals. And so the idea here is that you start with the bottom element if you want to go to the least fixed point, because you know the bottom element surely has to be in the least fixed point. And then you just keep applying the operator. In the cases that we are interested in for this talk, this will always converge infinitely many steps. But if you...
You're defining f of alpha plus 1 in terms of f of alpha.
Good point. So this is a clear... Disaster happened. So this has to be an alpha indeed. Sorry. So it's f of alpha plus 1 of f applied to f of alpha. Good point. And then at limits we would take the join. And then similarly for the greatest fixed point, we start approximating it from above, coming from the top, going down by again applying to f of alpha. There's no mistake. That doesn't happen twice as long as copy and paste exist. And then there is this other thing, which is the limit ordinal would take the join. So the one you approximate from below, the other one from above. And then for any monotone operator, there are ordinals such that you actually get the fixed point. This is the general theory. Okay.
And if you say that 0 is the limit ordinal, then it also does the right thing, I guess.
Yes.
Does it?
Yes.
But what do you do in the successor cases?
What do you mean you do this? There is no successor case with 0.
I see. Okay, fine. Yes. You mean, okay, fine.
You know, the empty, like the bottom is the empty join.
Yeah, okay, fine.
It's the empty.
I didn't understand the question. Okay, so of course, if you want to get rid of these two first questions, yes, you can kind of minimize the definition by not having these two cases. Yes. Good point. Okay, now let's go to the next slide, maybe. So now we want to actually, so this is what everybody somehow knows, I think, about fixed points. And I'm just using this as a motivation for games with infinite plays. So what's the motivation here? So the games here are played between two players in the whole talk. We only have a game between two players. In that first part of the talk, the players are called Eloise and Abelard. And the board positions are positioned basically in Eloise's positions and Abelard's position. Later on, Eloise and Abelard will be replaced with 0 and 1, just to make it easier. But on the high level play, we can just use Eloise and Abelard. And okay, so if you are in a position, so each position on a graph is owned by one of the players. And if you are in this position, then one of the players has to make a move. And with graph, I mean directed graph. So any kind of edge has a direction. So a play is basically just you start somewhere on the graph. Whoever owns that position has to make a move. Then whoever owns the next position has to make a move, and so on. And in this way, we can just make moves. And eventually, we have to figure out who is going to win. In particular, eventually, we have to figure out who's going to win the infinite games. And this is, yes?
What's it mean to win?
That's what we have to define, right?
What does it mean to win a finite play?
Did I say this already or not yet? So basically, later on we will avoid finite plays because we don't care about them. So basically, what you can win only what's called a complete play. Now there are two ways in which a play can be complete. One is that the game is infinite, the play is infinite. So once you have an infinite sequence, you want to say who is the winner. The other way of saying who is the other way in which it can be complete is that it reaches a position owned by one of the players, but there is no move for the player. So if there's no move left, we stopped somewhere, and then the player who is owning that position loses, because the intuition is this is the player who was supposed to move but can't, so he's stuck. So winners only make sense to define for complete plays. For finite plays, the player who is stuck loses. For infinite plays, this is what the talk is about in a sense. Sorry, I don't know what I'm. So it's kind of sometimes bad to have old slides because you at least disagree with one item. This does a lot of lifting here. I mean, because there's not much description here. This means, so the games that I just described, where with the complete matches I declare winners, if I now say, for the sake of the first part of the talk, that all of the infinite matches are always won by one of the players, and I will tell you in a second by which, then you will know that at any position of the game, one of the players will have a winning strategy. And that will be again made formal when I reach the parity games. But a strategy is just for a player a partial function that tells them where to move at a given position. And the game is consistent with the strategy if the play actually follows the strategy if it reaches that position. And winning would mean that any game consistent with the strategy is winning for the player. It's a winning strategy. No matter what the other player does, we'll end up in a play that is winning for the player. And for these games, you know that for the trivial ones, you know for sure that indeed always at each position, one of the two players has a memoryless winning strategy. And then for parity games, I try to sketch why that is still the case, basically. But let's not go ahead.
Is that a constructive either?
Is it what?
Is it a constructive either? Can we tell at any point?
Yes. So, I mean,
No.
well, not.
I mean, it's a choice principle, right?
Not on a finite game, right?
No, no, finite game, no. A finite game is.
Okay, now, I mean, if you go to infinite games, then indeed, then it's not constructive. But
chess, it's reputable which bank is winning strategy, but nobody is able to say.
But this is you are now talking about general kind of. I mean, there's a whole mathematical theory for the mathematicians like Guillaume in the house on infinite games. But let's not get drifted away into chess and checkers, because chess is not infinite anyway, unless you kind of no, it's not
It's
infinite.
not infinite, but it's also not quite a board game because repetition is
Okay.
important. So it's hard to like actually make the board.
Famous last words of let's not go down the road of chess and then in the medium. Okay, sorry. So now let's look at the following simple game. This is a concrete game, as concrete as it gets. No? It's a two-player graph game, and there are two types of the graph. Actually, I'm defining the graph here. So what has two types of vertices? Elements of a given set X, all of the elements of X are vertices, and all elements of the power set of X, so all subsets are also vertices of this game. And I'm defining what the graph is. The graph is at such a position, this player Eloise can move to a position of the other type. Such that X is an element of the operator applied to the set that Eloise moves to. So she can only move to those ones that satisfies this condition. Vice versa, if Abelard is in a position which is a subset, he can just pick any of those. And then we move on and on and on. So this is the defining the graph. And now indeed, with this game, we can define what's called the least fixed point game. And then Abelard wins all the infinite plays of this game. And with the greatest fixed point game, Eloise wins the infinite plays. So the idea is somehow that if you want to show, sorry, what does it mean? Sorry, did I say anything here? So this is what we define. And now important is, this is the goal of the whole story. Namely that Eloise has a winning strategy in the position in the least fixed point game, if and only if we are in the least fixed point.
Just to clarify, this game is bipartite, right? So like
Yes.
every time you're going into the other player.
But this is just I mean, it's not a restriction in general, but that one is, yes. You're right. Any other questions? No. Fred, you were looking very excellent. So the point here is that at the position, Eloise will have a winning strategy exactly in the least fixed point game if that point is part of the least fixed point. Yes?
So how does the player win infinite plays then?
That's a good question. I mean, we can't clearly wait for the infinite.
Yeah.
But the point is, we are not interested in winning. What we are what we are interested in is, does there exist a winning strategy? And this we can check. I can't play an infinite game either. No, I mean, however, yes, no, that's how it is basically.
What does the least fixed point game mean?
In which sense? So basically, there will be a concrete example of maybe.
This game is called the least fixed point game.
And what it means, what it means in a way is this fact here.
Definition.
Yeah.
I'm defining it like this, indeed. And then I want to prove the fact that, or I don't want to prove it, but this is like what you could prove. That Eloise has a winning strategy exactly if and only if the point is in the least fixed point for the least fixed point game, otherwise in the greatest fixed point.
Right.
I know it's actually defined something.
That's a lot of trying to frustrate by keeping the game going.
Yes, indeed.
And Louis has to at some point find,
Yeah.
find a position that Abelard it has to.
So the idea is indeed like
Yeah.
in the least fixed point game, Eloise is trying to convince by finally many construction steps we can reach something that includes that element in a sense. Whereas in the greatest fixed point game, it's like Abelard trying to say, if I apply that operator often enough, I can kick out that element that you're interested in. But if that kind of trying to get rid of it takes infinitely long, then still Eloise wins, right? I don't know. Anyway, so least fixed points are always the things. If you want to prove something is a least fixed point, you should be able to do that in the finitely many steps.
Maybe what's not obvious is that if you have a pair of strategies, is it decidable whether it is winning for some player?
I mean, it depends. Like, if the sets are finite, then it's definitely decidable. Yes.
Trying or not.
Yes, I also agree with this.
Depends.
Also, I don't know how you communicate that strategy, right? Move left if I don't know what hypothesis is true.
Your sense is very big.
Yes.
I was just wanting to double check something that somebody said that basically Eloise is looking for the empty set and to some extent for all of us, I forget their name.
It's more like Eloise is trying to prove something, and the false person is the Abelard is trying to disprove it. And in both cases, in the least fixed point game, Eloise is trying to prove that an element is in the least fixed point.
Yeah.
And then the other one is Eloise trying to prove that it's in the great fixed point. But it's always like she's trying to prove something, Abelard is trying to disprove it.
But I was just thinking, one of them is looking for wants to get to the position where you're on the empty set. The other one is looking for a position where X is not in F applied to whatever.
Yes, the top, that means the full set. I think I have part of the proof of that fact, in fact, on the... sorry, let's first look at the game. Not sure whether this is obvious. So this is the model. So this is... So we are talking now about Kupke models, briefly. This is a Kupke model where you have one state with one successor, two successors, three successors, but for each n you have a chain with exactly n steps going off that node. Whenever Ezra is looking like this, it makes me slightly worried.
Oh, no.
And then this one is the same model, but with the infinite, with one additional infinite branch. And now we're considering the following operator on this. It says, if we are given a subset of this, we map that subset to all of those x, such that for all successors, those successors have to lie in that subset. So if you want to have that set in modal notation, it will be box U, basically. I'm in that set if all of my successors are in U. And now we're interested, in fact, in the least fixed point of that operator. So the least fixed point of this operator would normally be written down mu x f of x. And so in this case, it would be mu x box x. And if you know something about this, basically, then you know that mu x box x is the formula that kind of characterizes exactly the things that are conversely well-founded, so to speak. So it means that there can't be an infinite sequence going out of a state. This one is fine because all of the sequences going out of x0 are finite. This one has a lot of finite sequences, but also one infinite sequence. So this one will be the least fixed point of this operator, while 0 is not in the least fixed point of this operator. And how do we see in the So in the first model, Elo is trying to prove in both cases that x0 is in the fixed point, in the least fixed point. In the first one, so she has to play some set such that x0 is in f applied to that set. if you look backwards, if you want that x0 is in f applied to that set, it means you have to put all of the successors of x0 into that set to satisfy the condition. The only thing that she can do with x0 is playing all of the immediate successors of x0. That's what's happening here. And then Abelard can challenge one of those. But by challenging one of those, he's committing to one of the branches. And now from that point onwards, there are only k steps left that can continue in this game until you reach a dead end, and that will be a dead end for Abelard. So therefore, you can prove that x0 will be the least fixed point. So Eloise just plays this, then waits for Abelard to respond, and then she's just accordingly kind of walking down the chain, and there are only finally many things that can happen. However, on the second model, Eloise in this whole set has to include that thing that starts the infinite branch. And then Abelard picks that thing. And now we are on the infinite branch, and on the infinite branch, it will always be, okay, Eloise picks the next successor and then the next successor, but we will never reach anything to no ending of this game. Okay. Not sure whether I want to go into the details. I also have here the details of the proof idea for the least fixed point game. Okay, now that is suppose, so the proof idea, what do we have to show? Suppose we are an element of the least fixed point. We want to show that Eloise has a winning strategy at X to win the least fixed point game. Well, if you're in the least fixed point, then you are somehow in the F alpha of mu for some ordinal alpha. And then, well, if alpha is a limit ordinal, or if alpha is not a limit ordinal, in either way, you can somehow go down one level in the generation of the least fixed point, so to speak, because you need a set. So, sorry, X is in F alpha, so that F alpha, if it's a limit ordinal, is just like the join, which is the union of all of the lower F beta. So because we know that X is in here, Eloise can play that set here. And then Abelard has to respond, and by responding, we are now moving to beta, which is strictly below. And because we're talking about ordinals, even though ordinals can be getting very big, you can only, and this is still something I don't really, I mean, I understand it, but I don't understand it, because you can only go finitely many steps downwards. So therefore, you know that after finitely many rounds, this game finishes. And Eloise never gets stuck, because we're getting in one round from something in the form F alpha mu to something in the form F beta mu. And you know again that because we are in F beta mu, again, Eloise will have a choice.
I'm confused as to why, when you go on forever, Eloise wins. Is it just, I guess, defined that way? Or?
Sorry, she loses, right? So if she wins,
Or Abelard, whatever the A one is.
Abelard, sorry. You can also call them Alice and Bob, but then they switch names. I mean, no, that's not what.
The A one.
Yes. What about?
I don't understand why Frall wins when it goes on forever.
Because
the E never gets stuck.
That's how we define winning.
Okay.
well, let's see on the next. Actually, that's a very good question because it's on the next slide. In some way, because so I just showed that if we are in the least fixed point,
Yeah.
we will finish. Eloise has a strategy to finish in final mini rounds. What, however, if it doesn't, if we don't have, sorry, if we are not in the least fixed point, my English is deteriorating by the minute. Anyway, then Eloise gets stuck and loses, right? We agree on that. But on the other hand, if she can find some set that satisfies the condition that X is in F applied to that set, then we know that that set cannot be a subset of the least fixed point. Because otherwise, I mean, X is not in the least fixed point, but X is in F of C. If X is in F of C and this was a subset, then X would be also in F of applied to the least fixed point, therefore it would be in the least fixed point. So therefore, if she can make a move, we know that that whole set cannot be contained in the least fixed point either. And that is the next. So then Abelard can take a point again, which is again not in the least fixed point. So basically the message is either Eloise gets stuck in finitely many steps because there is no such thing that can construct the X, or we can, if we somehow can find something that is not in the least fixed point, then Abelard can go on forever by always choosing something that is not in the least fixed point.
But can't you say the inverse as well? That like if we're playing from Abelard's perspective, then either you're going to choose one where Eloise can keep playing, or you're not. I don't know if that makes sense.
Okay, let's take that later maybe, I'm not sure.
Okay.
But so there's a definition that says if the game lasts infinitely long, Abelard will.
Okay. So that's
Yeah, the definition of big.
because it seems like this argument here seems convincing, except you could say the same for.
So it says.
No, but it's a definition indeed.
Sure. This is the definition for
Yeah,
what.
so the argument says that either player, like either player either gets stuck or can force an infinite play.
Yeah.
But only Abelard benefits from forcing an infinite play, because if Eloise forces an infinite play, she still loses. So you can always force an infinite play,
It's different
but that's only good for some.
win conditions with different players.
Yeah.
It's kind of
Okay.
the confusing part.
Indeed. Okay, so this was this game for both least and greatest fixed point. There was some advertisement, blah blah blah. I think we don't have to go through this advertisement much, apart from this is kind of indeed the crux of the game semantics for fixed point logic, such as the mu calculus. Like just this observation that you can characterize least and I mean, I learned the semantics of the mu calculus, the game semantics, without knowing this, which is much more difficult because where does it come from? But it's better to just start with least and greatest fixed point, and then try to lift this to arbitrary fixed points, as we will see in a second. Not arbitrary, but to nested fixed points. Yeah, so that is the reason why that is now interested to us. There's also questions about how to do the same thing if the lattice is not complete, but it's not something we are interested in right now, I think. So, okay, so this was just a warm-up, which brings me already to the end of my time. Anyway, so now let's move to alternating fixed point. So with alternating fixed point, I mean the following. Let's hopefully make sense of this. So suppose we have an operator which has not one variable, one argument, but two arguments. And it maps a pair of sets UV. So we are in this case on a Kupke structure. So we have a set of states and a relation on that structure, like in this picture with these arrows, where we had the operator box U, which was true if all of the successors are in U. There's also similarly the operator diamond U, which is true exactly if at least one successor makes U true. And there's the operator diamond V here, so to speak, which also says it's true if at least one successor is in V. And so once we have an operator with several arguments, what we can do is actually we can then combine least and greatest fixed points. So we can write down stuff like mu x, mu y, gxy. Sorry, yeah. So where the mu would bind this argument here, and the mu binds this argument here. And so, of course, now you can just, you know what the definition of least and greatest fixed point is, you know the sequence. What you can now do, of course, is just to calculate what that means. But for calculating what that means, you have to compute the greatest fixed point of the thing that maps x to mu y gxy. You have to then first, you start with the whole set, then you check what it means here. But here would just, in the first instance, the U would become the whole set. So diamond true, what you're looking for here would be some state that makes P true, and diamond some state. So it's a state that makes P true and has a successor. or you just unfold the least fixed point a few times. So basically, if you try to do the sequence argument, in the first instance, what you're going to compute with this least fixed point would be all the states that can reach a state where P is true and which has a successor. And then you can do the next iteration of the new, and then again do the computation. And it would be then all the states that can reach P, have a successor, reach another P, have another successor. And so over time, what you will get is, in fact, exactly those states where there's an infinite path along which P is true infinitely often. So this is something that you could not express, I claim, as a least or just the greatest fixed point. So it's really this interaction of the greatest fixed point telling you you go down the whole infinite path, and the least fixed point ensuring that every finitely many steps you reach something where P is true. So this is the alternation. And okay, so now I explained to you how to compute this in concrete terms. But the idea is, however, to give that a more intuitive semantics and also to be able to compute it efficiently. In fact, we move from the characterization a la Clean to the games. And now, however, for these games, it's not anymore the case that one of the players, so that in the game, Eloise will be still the player who tries to prove that something is in the operator, now in this case mu x, mu y, g x, y. But now it's not anymore enough to just say one of them win infinite games. Now what we have to make sure is that Eloise wins an infinite game if the most important variable, so to speak, that is unfolded infinitely many times is a new variable. Because this new variable in the kind of definition of semantics is also unfolded infinitely often. But it's only unfolded infinitely often because we are iterating the new infinitely often. And as part of the iteration of each new, we do finitely many mu steps. But there's no infinite sequence of mu's which is not triggered by a new. So we have to make sure that any infinite sequence of mu's, so to speak, is triggered by an infinite sequence of more important mu's. And in this way, we make sure that this is the proper, we are actually generating the fixed points properly.
I mean, who's responsible for choosing two Greek letters that sound so similar?
That's a good question. Also, I remember that there's this one famous paper about the completed Mu calculus, where one of the Igor Walukiewicz, he uses these colors. One of them is magenta, and the other one starts with N. And it took me a year to figure out that this was a reference to mu and mu. even though it's obvious. Anyway.
What are you start with?
I don't know. It was such a weird color that I thought, why on earth was he using this kind of color? Until I realized that this was a reference to mu and mu. Anyway, sorry about that. Okay, so this brings us to parity games. So the parity games are exactly the games that you just seen, with one additional feature. Namely, a parity graph game is somehow a graph game. So we have a set of vertices. Bloody hell. This is just complete craziness, right? Sorry.
I think if you click on the pen, then it turns into adaptations.
It's called a touchscreen, which you shouldn't touch it.
Okay, so this is, we have vertices, this is the edge relation of the game. And this is something which is called, well, so I don't know, you can call it well, let's call it the priority function. It's better to call it the priority. I think a lot of people would call it the parity function. But it's mathematically more sound to call it priority function. I shouldn't go on about this. Good. So it's just a directed graph indeed, partitioned into sets, as before. It's really like before, but now there is just a priority function. And a play is just a sequence of vertices such that indeed the I+1 element is reached from an edge by I. And it's complete if it's either finite and there is no move, or if it's infinite. So now I have the slides that I wrote only last week, which suddenly make more sense, to be honest.
Where was the parity used?
Sorry?
It wasn't, yeah.
And so far nothing is used in it. I think it's coming up here now, hopefully. So basically, we say that the player wins a complete play. Wait, is it sigma? Okay, now I shouldn't have. Yes, sigma wins a complete play, either if the last node is from the opponent. That's good. I was just sure that I would screw that up, but not really. Or if it's an infinite play, and I look like at the limit of this of soup. So basically, I'm looking at those priorities which occur infinitely often in the sequence, and take the maximum of those. And then I take to check whether they're odd and even. If the maximum is odd, then player 1 wins. If the maximum is even, player 0 wins.
Player 0 is.
It's in our case Eloise. So if you, but we could define it the other way around. But in all what I'm saying, I think of player 0 as Eloise. Yes.
The one.
It just becomes much more easier to talk about the opponent if you call them sigma and the opponent 1 minus sigma, because Eloise and Abel are quite distant, and I can't say 1 minus Eloise. Sorry? No, because so if we're talking about this, first of all, could only happen if the game mode is infinite, right? And I was not precise here. So if that game mode is finite, then the definition is fine. If it's infinite, we would require the omega to be a bounded, to have just a finite image, basically. Yes. I mean, I'm sure you could define it differently. Usually that's the assumption that is being made.
So it's an arbitrary graph, not necessarily generated by one of these linears.
No, the graph here is just arbitrary. So now I'm just kind of talking about yeah. But there's one thing I wanted to do which I didn't do, including an example, basically.
You can draw the word.
I can maybe. Let's see. Let's first go. Let's see whether we can still reach something. This is the definition of the game, and it's clear enough, I think. And now strategy for player sigma is just a partial function from the nodes of sigma to v, basically. I didn't write v1 minus sigma because it's not always bipartite. So anyway, that said, if this function is defined, then it has to be an actually a valid move. And then a play is consistent with such a strategy if for all the states in this play that belong to sigma, we have that the strategy gives you the next move. And then finally, if it's winning, if all plays consistent with it for 1 by sigma. I'm now just making kind of sense of the notions that I mentioned before. And then there is a theorem when you have a parity game, then the set of vertices can be partitioned into 2 sets, W0 and W1, called the winning sets of 0 and 1 respectively. And the rest is not so important, but on W0, player 0 has a winning strategy, on W1, player 1 has a winning strategy. Sorry, I just copied the full statement from the respective paper. But we don't necessarily need to discuss now that, I mean, this is useful to know in the proof that W sigma is a 1 minus sigma trap. It's like 1 minus sigma cannot escape from there. Sorry, I just need to now really rethink what I'm doing. Okay. How much time do you have?
It's 13:53 right now.
This is only part of the answer. No,
mapping the vertices to their respective 0 and 1.
Sorry, in the original game, where you mean the least and greatest fixed point game,
Yeah.
there the omega is kind of trivial, so we would just map.
Yeah.
So basically, that omega would either map all of the nodes to 0
Okay.
for the least fixed point game, or all of the nodes to 1 for the greatest fixed point game.
Yes.
Did I do the other way around? The other way around. We want to, Eloise should win the infinite match in the least fixed point, in the greatest fixed point game, so we want to give it an even priority.
Yeah.
But there the point is, because they only have one fixed point, we don't have to, that whole thing is just a hack, right? That's the thing. The whole parity is not really meaningful beyond the order. So this just introduces an order between fixed points. And so you could define that game instead of with numbers. You could just say that there's a certain order which allows you to order those things. But the numbers are just a hack. The numbers are just here by accident. It's not that the numbers have any natural meaning beyond making sure that 1 is bigger than 0. And it's also bad in the sense because that order, the dependency order that you're interested in, is not actually linear, but it's more like directed. So you are interested in a different order than what you do, but the natural numbers were somehow lying around. So why not using them, basically? Okay. So now, I don't know, I had that ambitious plan of proving that theorem, but I'm not sure whether I will manage to prove that theorem. So there are two ways. So there is now, this is a theorem taken from a paper from the 90s, where you can prove it just by, well, using some ordinals and showing that you can construct a sequence that converges to one of those two sets, and then ensure that everything works out fine. And there's another one using progress measures. The progress measure proof has a high-level structure which is more intuitive, I think, than this proof. However, in the interest of time, if somebody wants to see the proof, I will have to kind of postpone it, I think. I can do it for the people who are interested, but for now, I think that wouldn't make sense because I only have 4 minutes left. However, what I can say is, how do you prove such a thing? And there's something that is slightly curious about it, because we always prove stuff in 103 inductively, right? But why do we prove things inductively? Because they're defined inductively. However, in this case, we are proving its theorem inductively, even though it's not defined inductively. Because to prove that theorem here, that you always can split the set into 2 different winning sets, you prove it by induction on the range of the parity function. So if the parity function only has 0, you're back to the kind of to greatest fixed point game, basically, which so there's one important thing here. Did I not mention this? Yes, here. Without loss of generality, we assume that there are no finite matches. And then the case of equals 0 gets relatively easy to check because we just have to check for loops. But for the case n+1, we somehow have to do some work. And then it depends which player is the one which would win if we visit n+1 infinitely often. And then we cut down the overall sets into something that doesn't reach the n+1 parities. And then by induction, this set that doesn't reach the n+1 parity, we can already take care of. And however, there is some part of the construction that we have to do such that we make some progress. But basically, inductively, we will cut it down to a game which only n parities, apply the induction hypothesis, and then move on, so to speak. But that is something that I can show you if I have around 10 minutes time, I guess. But so this is this proof. That, blah blah blah. And then there's another proof what uses what's called progress measures. So the first proof that I tried to at least hint at is just it operates on the subsets of the model, and you kind of construct an ordinal sequence of sets, and this converges to the right thing. Progress measures is different. It just kind of locally looks at what you have to ensure to make progress, basically, towards fixed points. And so if progress measures, so you suppose you have D priorities, then a progress measure, you should think of operating with tuples of D natural numbers. So from 0 to D minus 1, if you have such a tuple, you can just order them lexicographically. Because you want to order them lexicographically, people who work with progress measures usually say that the most significant priority is now not the biggest one, but the smallest one. Because this doesn't really matter, but I think this is why they do it, because in the lexicographic order, the first entry is the most significant one. But however, in addition to the lexicographical order, you also have this thing, which is called small equal than I, where I is somewhere below. And so this only compares then the prefixes. So this I should go here, sorry. So remove this I can't do that with my finger. So basically it's just saying, instead of looking at the full sequence, we look only at the first I.
Well, quasi order.
Yes, it is. But so the idea here is that as soon as we are at priority I, we are only interested in the ones which are more important and not in the ones which are least important. That's why we can chop off the rest and don't care about them anymore. So the main node is now at the beginning, basically, and indeed we can reset all the least significant priorities. And this order to understand, if you understand this kind of order, which I now explain in a shitty way, however, this is really the crux of, first of all, showing this deterministic result for parity games using progress measures, but also if you look into proof systems for the mu calculus, this order also plays a big role, because you have to somehow, there's always this idea that, oh, we are now at a fixed point, now we can reset all the ones which are less important, basically.
Actually, it smells faintly like a baby house with a nation. Is that a thing?
I think if you see that, and if anybody can answer this question.
I mean, so when you're doing like various cut elimination with proof transformations, you also have this kind of measure, which is like something has to decrease, but then if one thing decreases, other things can increase. Some power of the
Well, isn't this just used for like showing that termination for rewriting systems in general? You use extensive.
Yep, that's another point where they use that thing.
Well, as you pointed out, it's basically quasi-order, so.
Yeah, I mean, well, I don't know if the quasi nature is often used in those, so I think that's kind of like a little difference where sometimes where you get like things that are like incomparable, but then you know, if there is like a big anti-chain, that you can't have big anti-chains in it, and it's just weird.
Yes. Okay, so now briefly just about, I want to just briefly get this, I think, hopefully there's no problem on this slide. So suppose we have a graph game with n priorities, blah, blah, blah. So then a function assigning to each node a d tuple of numbers is a progress measure if for all of the edges we have that row v is above row w. So you are above. But with respect to the priority of this one. So you just saw something and you have to be bigger or equal to the successor, but only with respect to the things that are more important than yourself. And most importantly, this inequality is strict if this is all. And so now the idea is just that if you could construct this, if you can show that there is such a progress measure, then you can also show that there are no infinite cycles which are odd. So that excludes all of the infinite cycles.
Is this equivalent to in the whole game the kind of extra stipulation you made about who wins in the infinite case?
Well, so what the condition there was that if I'm on an infinite game, and if the game is finite, I'm on a cycle, then I don't want to have a cycle where there are infinitely many, where the maximum priority is odd.
Yeah. But this ends up being the same as
This basically ensures that there is no such bad cycle. This condition is not the same. It's just kind of, if I could meet this condition, then there would be no odd bad cycles. Which is slightly too strong, so therefore if you actually want to talk about deciding who is winning a game, you need to be slightly smarter than this. You move to these kind of small progress measures, where you actually only take care of the odd priorities. So you only count the odd priorities. You count them because the idea is if you're an infinite one and you start the counter somewhere, and if there's an odd cycle, then it will run out of, you will run out of numbers, so to speak, and you are in the trouble. So if you can show that something like this exists, where you take care, where you always register the odd ones, there can't be an odd cycle. But clearly, normally in a game, we will have odd cycles. If we always only talk about parity games, that where all the cycles are even, we would not need much of machinery. But so what's happening here is that we will assign either a value or the top element, which means basically undefined. And so the ultimate idea here will be that if you can define what is called a parity progress measure, then player has a winning strategy exactly if the parity progress measure is defined on that state. If it's undefined, it means that it's undefined for a reason, because probably there was an odd cycle where you could not squeeze in the labels appropriately. Because the idea is always that for odd ones, you need to make progress. So I don't want to go through the whole definition here, but the main point here is if the current priority is odd, this is odd. Then the inequality towards the successor has to be strict, or we are just kind of already at undefined level. So basically, any odd cycle will push this to undefined. Push this, meaning there's a fixed point construction, which constructs the game priority measure as a fixed point. So you start by the function that is giving zeros to every, just tuples of zeros, and then you start iterating this function over and over again until it converges to a game priority progress measure, which will be exactly defined on the states which are winning for Eloise and undefined on the states which are winning for Abelard, or 0 and 1. Sorry.
Should the bottom one be the minimum of the maximum?
The bottom one, sorry, did I call it bottom?
No, sorry, I just, in the 3 cases.
It should be the maximum.
Okay.
It's like, because, so the idea is that if you're on a cycle, you need to kind of go down if you're currently odd. So if you were to go down, you can only make sense of that if you start already in plus infinity and then stay there, so to speak. Indeed, there would be another way of saying go down and reach minus infinity, but that's not how it's handled. Just said, I can only define it properly if I just already define plus infinity and then go plus infinity around the circle. That's, I mean, it's, yeah. A lot of those things are choices, however, but not all of them. Sorry, I think I better finish with this. I personally, I understand that proof now, but it's not easy to convey that feeling. So this construction is kind of curious because you get an operator for each vertex. And you start with the progress measure with assigned to each vertex just 0, 0, 0, 0. And then you have this lifting. For each V, you have a lifting. What you have to do now to converge to the actual progress measure is to apply the lifting for all V's over and over again. So now you don't have one. It's similar to the previous least fixed point construction where we just did one operator and applied over and over again. Now we just have a collection of those and apply it over and over and over again until we reach the joint least fixed point of all of those operators. And this will be then the progress measure that gives me exactly the states which are winning for LOVs, for 0, and or the ones which are winning for the opponent for 1. And all of what I tried to say is kind of contained in those papers when you want, if you wish. There's this paper where it all goes back to, which introduces the whole idea of using parity games in this setup, I think, from 1991. Then there's this proof that I only kind of hinted at, the inductive proof on the parities, which to show that you have determinacy and winning strategies for each of the players, which is this paper here, which is quite nice. Then the small progress measures, I think, were introduced by Eugensky in around 2000. And in fact, so this won recently a prize, this paper here, because indeed this shows that solving parity games meaning taking a parity game and deciding who has a winning strategy in which position, is quasi polynomial. So it's a big open question in this area whether that solving that game can be done in polynomial time, but it's basically close to polynomial time, but currently not in polynomial time. Indeed, and that's it. The question is, can one solve them in polynomial time? Okay. Erase quasi, because the answer to the first question is yes. I'm answering the long-standing open question to the first one. And then why do we do this? Because, I mean, so if you actually look into how to check the truth of a formula on a model, you take the model, you take the formula, you generate the parity game, and you solve the parity game. And so it would be nice to have a good understanding of this, maybe even to have a proper, like, the idea originally was maybe for somebody to program this in a language that is not just Java. Okay, anyway. And then there is, of course, there are variants of these games where you want to talk about quantities rather than just about true or not true, so to speak. And that was part of that Popple paper where they were looking into just general lattices. And then kind of the game starts with some kind of value. And if you can win that game, then you have certain lower bounds and things like this. So that's. And there's also a paper, by the way, on open parity games by our Japanese friends, who basically, indeed, if you set it up in the right way, then you can solve the components and then plug it all together. And that's it.
I have a question. Is ignorance
If you ask me about the proof, no, which one? What's the question?
not the question, that is up to you if you
That's a good, it gives me kind of a cop out.
So I was wondering when you were talking about least fixed point games,
Yes.
the proof in one direction, you're really using this characterization of least fixed points as the limit of the rest of the normal sequence.
Yes.
I wonder if there's a nice proof where you actually use the induction principle rather than.
I think the answer is probably yes. But I would need to think about it. But I think I have a feeling that 1/2 could be solved in this way.
I mean, you can show that like the winning set.
Ah, yes. Wait.
Or post fixed point. It's one of the two. And then that gives you one. Hold on, go ahead and button.
What does it give you then? Then it gives you basically that it's correct. Yes. That when you have a winning strategy, then yes, indeed. That is the thing you can do. So you need to show. You need to show that it's a prefix point. And it's clear that you can play the winning set because the actual thing that you have to play has to be contained in the winning set, so to speak.
Oh, and in fact, there is a very clear if you start with the winning set in the least fixed point, there's a clear winning strategy. Namely, always choose the least fixed point. And then Abelard will choose another point in the least fixed point. You just choose the least fixed point again.
No, but this is bad.
What?
Now you lost.
Oh, you're right.
I think we just both lost, basically. Okay, let's take
Okay,
that
let's
offline.
take it.
I have the feeling that one of the half can be done like this, but I'm not sure which one.
It would be nice if it was the other half.
Yeah, I think one half of this is just normal circuit, because I think you might even be able to like prove with Königslammer or Königslammer with this kind of thing. So
Yes.
I think there is this is an area.
Let's think about that nevertheless, yes. Thanks.